Okay, so usually at this point of learning about Stokes' theorem, some students start to wonder, wait, what happens if I wanted to evaluate this surface integral of the curl dotted with a normal vector, or another way of thinking that is the flux of the curl across a closed surface? Like, how does that relate to what I've learned from Stokes? And so let's visualize what this is really a flux integral, flux of my curl vector field. In fact, you could think of this vector field right here. We could think of that as G. And when I'm talking about a normal vector for a flux integral, we're assuming that the normal vector always points outward. And so that's the default assumption in this setup, is that at any given point on the surface, we're finding the normal vector that points outward, or we're using the normal vector that points outward. Okay, so we have a couple ways we could think about trying to do this surface integral. Method one is we could say, well, I could break it up into two surfaces, the top half surface and the bottom half surface. So like the top hemisphere and the bottom hemisphere. And then I could do this surface integral over both of those. So let's write that out first. And then actually, just to make my notation a little even more accurate, I could have put a little circle, closed circle like this around the surface since it was a closed surface. But anyway, I've broken it up into these two surface integrals. And so let's assume that this vector field is such that Green's and Stokes' theorem holds, i.e. that my components of this vector field are continuous and have continuous partial derivatives. So if I can use Stokes, then I can, instead of doing the surface integral right here, I can do a line integral over the boundary. And notice the boundary of the surface is just coming from this curve right here, this circle. That will now be the boundary. So I can write this as the circulation integral of my vector field over this curve. And then similarly, what's going to happen with the second integral, recall that the way Stokes is oriented is we are assuming your orientation of your curve C is such that it relates to your normal vector using the right-hand rule. So you need to curve your hand around the curve, and then your thumb will point in the direction of the normal vector. So going from here to here, that works well, because when I curl my hand around this curve C, my thumb is pointing outward. But now if I would like to actually use Stokes for this integral, and I know that my normal vector already points downward, it means I'm going to need to go the other way on the curve in order to be able to use Stokes. And so I'm going to now integrate around the curve, and I'll just put negative C. That means we're going the other way, and I'm integrating the same thing. Okay, and I'm adding these two together, and so we know that that's just going to be the opposite. This integral will be the opposite of this one, and so we're going to get 0. So this is one way to see it. And again, this is assuming that we have continuous partial derivatives for our function, or our vector field f. One other way we can see it, we can actually connect it back to the divergence theorem, which is a pretty cool connection. So here's the other way you can think of it. I could apply the divergence theorem. Let me give myself a little bit more room. Okay, I got a little bit more room. So, and I also put the conditions that I should have put in this problem, because we can really only use these shortcuts if we know my vector field has continuous partial derivatives. All right, so method 2 is let's actually apply the divergence theorem. So recall divergence theorem. And I'm just going to write it here for a general vector G here. The flux across the surface is going to be equal to the integral of the divergence over the interior. And so over the interior, I'm going to have divergence of G, and then I am integrating this. And so let's take this. This is divergence theorem. Let's take this now and replace, where I have a G, replace that with the curl of F. because that's really what the G represents in this analogy over here. So you can think of this like my G, which means by the divergence theorem, this should be the divergence of the curl of F, and then evaluated over my region. Oh, and I'm calling it E, not D, so let me fix that. That's E here. Okay, now this is a great problem to actually do. I'd like you to try finding the divergence of the curl for any generic vector field. And so put it on pause and see what you find, and then we'll come back. Okay, so notice what happens given a general vector field if we find the curl. So I've just gone ahead and done this without drawing out the determinant. Now I want to take the divergence of this vector field. And so again, recall to find the divergence, I'm taking the partial of this one with respect to x. So now I'm going to get r sub yx minus q sub zx. And then I'm adding it to the partial of this with respect to y, p sub zy minus r sub xy. And adding that to the partial of this with respect to z, minus p sub y z. And if I have continuous partial derivatives, then Clairaut's theorem is going to hold, and these will cancel. Here, 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 and we're going to see that the divergence of the curl will be 0. So that we can go back to this method here, and we notice that this is 0, which is how we get back to the same answer that we saw in method 1. So this should be a nice way to connect or think about both divergence and Stokes' theorems and which surfaces they apply to and which ones they don't, and how they are interrelated when you try to apply them to a closed surface like this.